Our last speaker today is my colleague David Hoffman of Stanford University, who will talk about limit laminations in Euclidean and hyperbolic space.
Thank you, Brian. Is this on? Can you hear me? Thanks. I'd like to thank the organizers for being here. I can't thank the scientific committee because I'm on it, although I can tell you all the good things you've seen have nothing to do with me. Everybody else worked, I didn't. Okay, so I'll try to make up for it. Or, well, maybe I shouldn't continue that. So this is a joint work with Brian. And what I'm going to talk about, the main things I'm going to talk about are things I don't completely understand. Most of you have heard me talk before, probably know that I do that occasionally, but this time I know I'm doing it. Okay, so let's ask a very, very general question. What properties of a minimal surface provide a bound for Gauss curvature at some points of the minimal surface? And another related question, given a sequence of embedded minimal surfaces, how many times do I have to push this to get the next? It's this?
Point it there, sir.
Okay. When is there a subsequential convergence? And what kind of limits can occur, and what kind of curvature blowup is possible. So let me just remind you of something simple but useful. If you have a uniform bound on curvature of a family of surfaces, let's say in R3, let's say in the neighborhood of a point, then on a possibly smaller neighborhood, all these surfaces look like graphs. So curvature blowup violates this, but if you have a uniform curvature estimate, you know for this sequence you're going to have nice behavior. Graphical behavior to me is nice. So let me tell you one well-known result in this area, and that's this. Let's take a minimal surface sigma and let calligraphic B, R, be the intrinsic ball of radius R centered at P on the surface. It's a famous and great theorem of Rick Shane that says if you have an orientable, stable minimal surface, you don't need orientable. I think it's a result of Antonio Ross. Take a point on it, and then there's a universal constant C independent of the surface and the point, such that if that ball doesn't touch the boundary, it lies entirely inside the surface, then on the ball of half the size, you have a bound on the curvature. So there's some constant C in the bound is a constant times r to the minus 2. Okay. So you can prove things with that, and it's a famous theorem of Doris, Fisher, Colby, and Rick, and Del Carmo and Peng, independently proved. The only complete stable minimal surface in R3 is a flat plane. Well, by completing this, you can get a ball of any radius r that doesn't hit the boundary. The boundary is at infinity. There is no boundary. So you have this estimate for every r on the balls of radius r over 2. And so making r go to infinity says the curvature is 0 everywhere, and that implies it's a flat plane. So that's just a bit of a warm-up. Let me repeat the question before. Given a sequence of embedded minimal surfaces, when is there a sequential subsequential convergence, and what are the possible limits, and when can curvature blow up? So let me tell you again, Brian did this, but let me do it again. Suppose I have a nested sequence of sets. For the moment, think they're all the same set. So U1 is U2 is U3 is U. And I say, if I have a sequence of properly embedded minimal surfaces, I don't need embedded here. We say this curvature blow up at a point P in that set. If I can find Pn in the surface Dn, and Pn converges to P, and the norm of the second fundamental form tends to infinity. That gives you that the curvature, Gauss curvature, tends to infinity. Okay. Okay, so if I have such a situation and I stay away from the set where the curvature blows up, I can find subsequences that converge to a minimal lamination of the set U minus the curvature blow-up set. Well, what kind of sets K, curvature blow-up sets, can arise? And what's a lamination? So let me answer those. Let me answer the second question. The first question is, there's more known about it now than there was a year ago, but it's still an interesting open question. Let me give a definition by first giving you two examples. Take the standard vertical catenoid, or as Brian reminds me, it's a catenoid with a vertical axis. Brian tells me that the catenoid at the left is a horizontal catenoid. The catenoid on the left is vertical, but it's so old that it's tipping over. Harold and I understand this very well. Okay. So rescale it by multiplying by 1 over n, and sigma n is the rescale catenoid. That's about n equal 10 on the right. And keep going, and every point away from the origin, I'm assuming that the origin is right at the center of the disk that's on the plane of horizontal symmetry of this surface. The curvature is uniformly bounded. In fact, it's going to 0. But there, as you can see, the curvature is blowing up. And the blow-up set is exactly that point. And the limit lamination consists of, in R3, consists of one leaf, which is the horizontal plane. It's covered twice. And the convergence is smooth away from the origin. Let's look at another example, and this is the most important example. There is a vertical helicoid. Old age has not hit it yet. And here's the same thing scaled by 1 over n. So what happens is that if you're off the vertical axis on the helicoid, and you scale it like this, the surface very rapidly, you're pulling in points from infinity where it's flat, and the curvature is going uniformly to 0. But on the axis, it's spinning around. The normal is spinning around faster and faster. The curvature is blowing up. So what you see is what I just said. You're going to see, you can literally see that it's going to a foliation of R3 minus the axis by horizontal planes. The curvature blow-up set is the axis. And you can extend those planes through the curvature blow-up set smoothly. But the convergence is not smooth along the axis. Okay, so let me give a formal definition of lamination. It's basically, as Brian said, it's a foliation minus some leaves. So it's a collection of smooth disjoint surfaces such that the union is relatively closed, and then it has a local structure. And here's a local structure. You can find a neighborhood, around any point, you can find a neighborhood in U such that coordinates take the leaves into horizontal lines. So that doesn't say that a horizontal line going through is on a different leaf than another horizontal line going through. It could be that, pick your favorite horizontal line, it goes out over here, it does something else, and it comes back through at another line. It just says this is the way it looks locally. But what I want to emphasize is this. Gee, does it say this there? Let me see. Yeah. So this closed set T might have limit points. And those points correspond to lines, horizontal line segments that are limits of other line segments. And I'll call those leaves limit leaves. Okay. Okay, so let's now think about the curvature blow-up set in a simple case. A convex domain whose closure is compact in R3. So take a sequence of properly embedded minimal disks whose boundary lies on the boundary of this set. And I'm going to call it a ball. You should think of it as a real ball. It's the right image to think of. Well, you get convergence away from the curvature blow-up set, as I said, to a lamination. And I'm repeating some stuff that Brian said. I didn't know he was going to say all this, but let me say it here again. Suppose there is some curvature blowup. A great theorem of Brian's is that curvature blowup lies on a C1 curve. That uses strong results of Kolding-Minkowski, the most important of which I'll tell you in just a minute. Bernstein and Tenalia proved that even if you start with well, Brian and I showed if you start with disks, you might get an annulus, a minimal annulus in the limit. Bernstein and Tenalia, again using strong results of Kolding-Minkowski, showed that you can't get anything topologically more complicated than that. And then it's an observation, I think, of Brian that in this case, if you have a point in the blow-up set, you have a minimal embedded disk going through it. And that curve, the C1 curve, is orthogonal to it. And if you get the whole curve, then, in fact, you get more than a lamination. You get a foliation of the complement of this curve gamma by minimal disks. OK. Brian and I proved a number of years ago, in the simple case where you take the unit ball, or let's say a finite solid cylinder, I'll call that B, with axis Z. So it's a region in space that's invariant under rotation about the axis Z. Take any closed subset of Z, relatively closed subset of Z, can be realized as a curvature blow-up set. And in this very symmetric case, through every point in the curvature blow-up set, the disk, the flat disk orthogonal to Z through that point is a limit leaf. In other words, the other leaves are spiraling into those disks. I'll say more about this later. Previously, Kolding-Minkowski, Kahn, and Dean did this for k equal to a finite number of points or line segments. But here, we can get any closed set, and it could be a Cantor set. So things can be quite complicated. OK. Let me tell you what I think is one of the more amazing theorems of the last 20 years in differential geometry, the Kolding-Minkowski global limit lamination theorem. Suppose now, instead of having one set, we have an exhaustion of R3 by balls. UN is contained in UN plus 1, and the radii is going to infinity. And in each one, we have a disk. We have a simply connected minimal surface that's properly embedded, and its boundary lies on the boundary of the ball. Well, let K be the curvature blow-up set, and script L the limit lamination of a subsequence. Their theorem says, with a little addition by Bill, Bill is gone. OK, good. I can say anything now. Is he really gone? He is. OK, if the curvature set is non-empty, if it contains even one point, then K is a line. Think of it as a z-axis. Rotate everything. It's a z-axis. And L is a foliation of the entire space by horizontal flat planes that meet that line orthogonally. It's all you can get. And that's precisely what you get when you scale down the helicoid. So this is the only example. That's remarkable. OK, let me tell you about the one-sided curvature estimate. I wasn't thirsty till I made that joke. All right. So consider a ball of radius r. To get this into your head, if you don't already know it, let r equal 1. So you have a disk in the ball. Its boundary is on the boundary of the ball, and assume it's in the upper half ball. That's this statement. There exists universal constants, c, perhaps very big, and epsilon, perhaps very small, such that the curvature on a ball of radius epsilon is bounded by c. The r is just what I can do by scaling. So for the unit ball, it says as universal constants such that if you have this piece of the surface getting near the origin, with an epsilon of the origin, in there, its curvature is bounded, no matter what. Okay. Okay, so let me say that the one-sided curvature estimate implies the global limit lamination theorem. This is something that Brian pointed out to me. So scale the ball to be size n, and if the one-sided curvature estimate fails, you can put epsilon as small as you want and c as big as you want and still get an embedded minimal disk that will violate that. So I'm going to let epsilon equal 1 over n squared. Epsilon equal 1 over n squared and c equal n cubed. So if the one-sided curvature estimate fails, you can get a disk in the upper half ball of radius n with the property that its curvature is bigger than n. So r to the minus 2 is 1 over n squared times c is 1 over is n. And when I multiply this by r, I get n. So at a point P in this ball of radius 1 over n, I have big curvature. Okay? So now this is going to be my sequence of embedded minimal disks. So I take a subsequence, and I notice that near the origin, I always have points where the curvature is as big as I want. So the curvature blow-up set at least contains, at least contains the origin. So the limit lamination theorem says, however, that if you have a non-zero curvature blow-up set in a situation like this, you must get the whole line, and the leaves are parallel planes orthogonal to that line. But look, each of these disks lies in the upper half space. So there are no leaves in the lower half space. That's a contradiction. So the global result implies the local result. Of course, the local result was used to prove the global result. So for the purposes of this lecture, they're equivalent. Okay. So let me tell you that this theorem is not only great and beautiful and surprising in itself, it has very, very strong consequences. First one is this. Take a properly embedded, simply connected surface in R3. You don't know what it is. Intersect it with a ball of radius n. And then, take that surface and scale it by 1 over n and intersect it with a ball of radius n. Either you have no curvature blow-up, in which case you know what's going on, or you have curvature blow-up, in which case what you're doing produces a limit lamination with a singular set that's a line, and leaves that are all limit leaves orthogonal to that line, just like you have in the helicoid case. And they use that information to prove that you started out with a helicoid to begin with. This is an amazingly strong theorem. By the way, Brian and I think Antonio Ross asked the question whether this is equivalent to the limit lamination theorem. That's unknown. But that would be nice. If this is of the same order, the same power as those theorems. I don't think that that's known. Okay. Bill and Harold proved another great result. It goes like this. Suppose I have a complete minimal surface in a Riemannian free manifold. Well, in a Riemannian free manifold, this Euclidean one-sided curvature estimate since Riemannian three manifolds on the very small are like Euclidean space, you have it for sufficiently small balls. So they used the one-sided curvature estimate there to prove that if you take the closure of that surface, remember it's complete, so it might have limit points in the space, but the closure of it is a lamination. It has a structure. Provided you have bounded the hypothesis is you have bounded injectivity radius on the submanifold, on the surface. And as a consequence of that, because surfaces of finite topology have bounded injectivity radius, you can show that you can give another proof of the Calabi-Yau conjecture, that if you have finite topology, you can use this theorem to show that if it's not proper, it has a closure point. That closure point's in a limit leaf. In R3, that limit leaf has to be a plane, and you can argue from that, again using the one-sided curvature estimate and the argument that I understand, to show that you get a contradiction. So this is really strong stuff. Okay, so I have trouble understanding stuff where there's no examples, and Brian and I looked for a class of surfaces that was simple enough so that we could analyze what happened with them, but complicated enough so that something happened with them. Let me tell you what that class is. So let's take the vertical axis z and take the unit ball or a solid cylinder with axis z. And we want to assume that D is a properly embedded minimal disk with these properties. First of all, it contains the part of the axis that's in D. And second of all, if you rotate about Z, that surface, you get a foliation of B minus the axis. So here's two examples. First of all, the helicoid is such an example. You take the helicoid, just look at the part that you get by choosing one component of the helicoid minus the axis. You rotate it around, it foliates space minus the axis. Here's another example. I call, for the purposes of this lecture, the surface a theta surface. I'm going to save energy and your time by not telling you why I call it that. Okay, we prove this theorem. Here's Z, and let's say you're in a rotationally symmetric, compact, convex domain that contains Z. And it is symmetric by rotation about Z. Think a ball or a cylinder. Okay. So this is the result I quoted before. Take a relatively close subset of Z. There exists a sequence of embedded minimal disks having this property, with curvature blow-up is precisely that. A subsequence of them will converge to a lamination of the space minus the curvature blow-up points, whose limit leaves are rotational minimal surfaces. In this case, that just means horizontal disks or minimal annuli of rotation. In other words, pieces of a catenoid. The curvature blow-up set consists precisely of the centers of the disks that are limit leaves. And it's a little hard to say, so let me just draw a picture. So here's a ball. I might get this as a, well, say I get this catenoid and this disk here. So these will be limit leaves. I'll get one leaf up here. It always contains the axis that spins down to this plane. I'll get another leaf that also contains the axis, so it's rotationally symmetric, that spins up to the plane and spins out to these catenoids. Well, it doesn't look like that. In fact, it's hard to draw how it looks. It's just one leaf inside of this spins out. And I'll get another leaf over here that spins out to this catenoid. And since when I rotate it, I might get a second leaf. So there might be two leaves here. There's one leaf in here. I want to emphasize that for a reason you'll know in a minute. So let me just point to it. I get one non-limit leaf if the domain in the ball minus the limit leaves has points on the axis. And I get two otherwise. And rotations of those surfaces, these surfaces have the theta property, they're going to foliate the regions that they're in. When you're out here, you get two leaves. One is the rotation by pi around z of the other. Okay, so that scares me. It means I have to show you how to do this. So let's say I want to get in K, let's say I want to get these 2 points. Here's Z. Say I want to get this point and this point. Notice I have nothing special in my hands. I'm just going to start here. I'm going to take this axis as part of a boundary curve. And I'm going to spin around. And when I get down to the level of this point, I'm going to spin around like crazy. When I pass it, I'm going to slow down. I get to this point, I get really excited. I spin around a lot. That's a lot. I come down. It's a finite curve. I can show that that actually bounds a unique, stable, minimal surface. And then I double it by Schwarz's reflection around this axis. And that's going to be my D end. And what I'm going to get is a surface that spirals down to this plane, a surface that spirals up to this plane, and something in between here that spirals up to this plane and down to this plane. I'm not going to tell you yet how I get a catenoidal leaf. Okay. Now I want to use the same procedure to do something which leads to a question. Let me see what I say there. So let me do this on a cylinder. I'll take a cylinder of radius capital N. Maybe I'll make its height 2n. And I'm going to focus on this disk in here. I'm going to come down from the axis, and I'm going to spin around a bit. When I get in here, so my angular speed will be approximately 1 here. Here, my angular speed is going to be approximately n squared for some other n, lowercase n. And here, this will be maybe 1 over n. And then here, I'm going to slow down. So angular speed, about 1. So all hell breaks loose here. And then I calm down and come down. I solve this boundary value problem. I can as a unique stable solution. I double it, and I'll call that disk DNN. So what I know is that I'm forcing the curvature to blow up at the origin. If I fix capital N and let little n go to infinity. Now, I do this for each capital N. And I take the disk D and N. So the cylinder is getting bigger, and I'm spinning really fast near here. The curvature is blowing up near the origin in the sequence. So the curvature blow-up set for this sequence contains the origin. But the Kolding-Minkowski limit lamination theorem says that since the curvature blow-up set is not empty, the curvature blow-up set must be an entire line. And since I know for surfaces like this, it has to be, it's going to be the entire z-axis. Yet, even though I'm getting farther and farther away, up here, at distance 1 over n from the axis, my boundary values are behaving just like the helicoid. So according to the limit lamination theorem, that says as I get farther and farther out, it doesn't matter how fast I could go. I could make this to the 77th. I could just really spin a lot here. The curvature is going to drift away. It's going to drift away so much that in the limit, the entire axis is the curvature blow-up set. I don't understand how that could be. Maybe there's some estimate that goes with the Kolding-Minkowski theory that says the farther away you get, the less control you have. Some quantitative estimate. So I'm not saying that this gives a counterexample. I'm saying that this shows that it gives a result that's not intuitive to me, and I would like to have some hard analytic estimates that tell me, that's what's happening. I didn't know that. OK. So let's say you ask the question in the context I was talking about these theta property surfaces. Let's say, gee, could I achieve this catenoid in these disks or a lot of disks and everything? What are the limit leaves you can achieve? So that's a somewhat different question. And remember, I emphasized that if you look at the limit leaves, if you have such a lamination, it has limit leaves, they divide the set you're looking at, the ball B, let's say, into regions inside of which there are non-limit leaves whose rotations foliate. So this is part of the theorem we proved. You get stuff like this. OK, so rotations of the limit leaves produce a foliation of B off the axis, and this defines a calibration. So if you have a calibration and you have a finite set of limit leaves, let's say script A, and another set of limit leaves, script B, that are surfaces of rotation 2 with the same boundary circles, and I want to say with the same orientation, then the ones that are actually leaves of this foliation that gave you the calibration, they have area that's less than these other ones with the same boundary, and they're strictly less than that unless these other ones are also leaves that help you define this calibration. So let me show you how we can use that. OK, so let me give you another example. So again, I'll take a cylinder. I'll take 2 points that are close by. Here's the axis. I'll take these 2 centers. And again, the disks are going to come down here. They're going to go wild here for a while, calm down. I'll move this a little down so I can calm down for a little while. Then go crazy again. And then calm down. So this is dn. Okay. So this is going to have curvature blow up. Maybe not. I don't quite know what happens, except I didn't do what I wanted to do. So let me analyze this. There's curvature blow up here, as I said before, and I'm going to get these two disks. What I want to do, and excuse me for screwing this up, here are the two levels. Somewhere in the middle, I'm going to come down, and I'm going to turn around and go the other way. And then get very, very crazy around here, and then calm down. So if I do this for a while, on the boundary, on the cylinder's boundary, I'll get something up here. I'll get a limit circle that's oriented this way. And at this level, I'll get a limit circle that's oriented this way. So I asked myself, what am I going to get? I could get two disks, oppositely oriented, because the boundary circles have to have a boundary induced by the orientation of the disk. Or I could get a catenoid. And this area minimization property that I just showed that came from this calibration discussion says that if these circles are close enough, clearly the catenoid has less area. You have to get the catenoid. So that's how we show that you can get catenoidal limits to sequences of embedded minimal disks. So how long will it take me to remember? I have to go the other way. We can do this in hyperbolic space. Exactly the same argument. And let me tell you what the argument will be and try to explain part of it here. Here's a model of hyperbolic space, the Poincaré ball, with this well-known metric. Here's a model of hyperbolic space, the upper half plane, with this well-known metric. Can you read this, Harold? Good. Here's a blue line, a ray coming out from this point going up. That corresponds to this blue ray. And now I want to make a model of hyperbolic space that has all these blue rays parallel. That's not making any sense. This isn't right. This isn't right. Let me just try to see if I can recover what's right. Here, these lines are orthogonal to the hyperbolic planes that are there. Therefore, you have to have the same behavior here. So be orthogonal to this. And these surfaces, these totally geodesic surfaces, correspond to the disks here. I'm having brain freeze about where this line goes. I suppose it has to go up to the other. Yeah. So yeah, it's curves like this, right? I know how to solve this problem. Okay. So these lines go to the point at infinity. Each one of these lines go from one point on the boundary to another. That's what's happening here. Okay, so this metric is not a product metric, but vertical translation is an isometry. So if you move up a level t, it's an isometry. So this warped type metric is it's not a product metric, but vertical translation is an isometry. I prefer to work there. Okay, so what I need to show here is that I can get exactly the same picture. I'm going to get a limit leaf, a single limit leaf that looks like this. It's a minimal, it's rotationally symmetric minimal annulus. I'll call it a catenoid. In the interior, I'll just get one leaf, one non-limit leaf. And in this in this region that looks bounded here but isn't because it goes out to infinity, I'll get two leaves. Exactly the same as I did in a compact set in Euclidean space. What does this say? It says if I look at one of these leaves here, that their surfaces, they're simply connected. And they're minimal. And they're complete. But they're not properly embedded. They have in their closure this catenoid. So this Calabi-Yau conjecture is false for hyperbolic space. I think this was first proved by pushing hard on the button. Jesus. By Boris Kuskeneuser. Entirely different methods. Okay. So I just went from Euclidean space on a compact region whose closure is compact and a convex region to hyperbolic space. It's a lot of hand waving. There are two problems. Okay. Our existence theorem requires that the domain be mean convex and compact. Hyperbolic space is not compact, and it's not clear what you would mean by mean convex boundary. Okay, so we attack this problem by solving in finite balls inside and taking limits. And we use results of Hartlin and Tonegawa to show that we can produce these theta property surfaces by drawing curves on the boundary. Okay, so that's one part I won't talk about too much. But another part is this. In order to get a catenoid leaf, I needed some area minimization property to rule out the possibility that you might get things that are simply connected. And this catenoid, if this were a picture of a Euclidean cylinder, this catenoid would have finite area. These disks have finite area. And, but in this hyperbolic model, they have infinite area. How am I going to show that if I'm careful, I can rule out the disks and get this catenoid? And the solution was talked about a lot by Maze a little while ago, a couple days ago. It's a marvelous idea by Rosenberg and Collin. And they were looking in H cross R. They were looking for domains bounded by geodesic polygons in which you could find a minimal graph, a Shirk-like graph that went up to infinity. You needed some conditions on this geodesic polygon, but all of these geodesic polygons went to the boundary, and they had infinite length. So you cut off by horocycles. And horocycles have the property, a very nice property that I'll tell you about in a minute, that Maze told us about in beautiful detail that allow you to do it. And we use that idea. So let me tell you how we use that idea. Okay, so let's take this model and say we want to find surfaces that are surfaces of rotation. By the way, if I have a surface bounded by two circles on the boundary, in this model, two parallel circles, you can use a version of Alexandrov reflection to show that it has to be a surface of rotation if you assume it's an annulus. Let's keep it simple. So we want to look at annuli. Therefore, we take this space with this metric and mod out by rotation. And so we just mod out by rotation. We get an infinite strip. And on that strip, if we take a curve, I want to write down a metric here which gives to the length of the curve the area of the rotational surface I would get in hyperbolic space. And if I write the curve as a graph, if I parameterize the curve, this is what I get. If I let it be a graph over one of these lines that correspond to hyperbolic planes, then this is just tau, so r dot is 1. And I just have basically something that involves a single, a single function u. Then I can write down this metric. And I can look for, you can use the Euler-Lagrange equations to get geodesics. So geodesics in this metric is a special form. I lost what I did. Anyway, there's something here. Correspond to minimal annuli. So my problem of finding minimal annuli in this space reduces the problem of analyzing geodesics in this metric. I have the metric completely written out. I'm not going to write it out. It's complicated. Let me tell you about the metric. So this is the picture I want. Instead of analyzing surfaces of rotation, I'm going to analyze curves here. OK, so I'm going to assume that the surfaces of rotation are given by graphs. I can prove that, or either by doubled graphs. So I'm going to get a graph of a function that's going to give me a geodesic. I'll let this be tau. And then I ask myself, follow this out to the boundary. Look at all the curves. Look at all the geodesics that go to one particular boundary point. So this point is 0, 1, 0. Variables are t and tau. And I find that every geodesic that goes to the boundary is the graph of a function u of tau. And it's on an interval between r and 1. And u, for any r, u of 1 is 0. The derivative there is 0. And it blows up at r. So for each r, I have one that blows up at r. U dot of r at r is minus infinity. So this is a picture of what the geodesics are. since these are totally geodesic planes, I can reflect. So that's a picture of a typical geodesic. Every geodesic is going to look like that. So I want to define something really big. I'm going to let A of R equal U R of R. So in this case, this is U sub R, and this is A of R. So I'm going to get some curve that looks like this. So here I'm going to graph A of R. This is A of R. So here's a variable R. And a typical geodesic will rise, 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 rise. So you hit this perpendicularly, and then I'd reflect at this level and go like that. So this is, by abusive notation, I'll call this gamma of R. So I get a double graph. So I then want to know, do these geodesics foliate? And I want to tell you that this picture is correct for A of R, at least for a while. So I take this metric, ds tilde, and it's a metric on a surface. I can compute its curvature, and it turns out that this curvature is negative if R is bigger than square root of 5 minus. So on some strip, let's call this R naught. So on some strip, R naught this is negative. This immediately tells me that if I take any R smaller than this, a geodesic that looks like that, it's stable. I don't know the right way to say this. If I look at my notes, I'll confuse myself. Let me just say that I claim that this picture of A being a decreasing function when you pass R naught has to be the case. Let me draw that picture here in detail. I'll just take this over here. Let's say A looked like that. Then I'd have a geodesic that went like this, and another geodesic that went like this. Now, vertical translation is an isometry, so I'm going to take this geodesic and translate it up a little. And you'll see that the up translation now crosses this other one twice. So the green geodesic, the original one, and the vertical translation of the other one cross twice. So if you're in a region of negative curvature, you have the following problem. This region bounded by the two of them has to satisfy the interior angles equal the integral of the Gauss curvature, which is negative on that region. That's a contradiction. So these curves foliate the region for a while. In particular, they're stable. So there are catenoids that are completely stable. And that's the picture to the top left. There's a foliated region. And then if I take the other geodesics that go out until they come to their vertical point, I can foliate a region that continues that. I can reflect in the horizontal and get a picture like that. The red curves now are the orthogonal trajectories. And that picture contains an important piece of information. It says that for a while, the orthogonal trajectories all go to that original point. So I get geodesic orthogonal coordinates, and those have a very important property, the same property that horocycles have. And so I'm in, okay. So almost, or we are out of time?
Well,
Are we out?
I mean, it's 55 minutes.
Okay, I'll stop. You can replicate what Rosenberg and Colan did and Mazet and Rosenberg did to have an area minimization condition by cutting off these infinite geodesics to make things that have finite lengths. If you cut off by one of these red curves, it doesn't matter. If you have an inequality that corresponds to an area inequality, it doesn't matter which one you cut off on. So that's how we go from this finite area minimization condition to a situation where the things you're trying to compare have infinite area. So just a little bit more. That's a computation of this curve A of R. In various parts of the literature, it says that that's not known to be true, and that is true. I don't know how to be true. There's various papers that claim it's true by doing a calculation I can't follow, or by not doing a calculation and quoting ones, others that don't claim it's true. That would say up to the maximum you have stable geodesics. The ones that go down by exactly the same curvature argument I gave, not the curvature inequality, but the argument involving Gauss-Bonnet, are unstable. So that would say that for these circles, you'd either get no solution, for values that are too high. For values that are too low, let's say this is always the base and that's the height, you get two solutions and then one unstable one. That's not known. I'm going to skip this, but you can compare now results in hyperbolic space and Euclidean space and see that things are different in hyperbolic space. Just want to, okay. I want to tell you about this. This is not part of my talk, but it's part of something I realized coming here. And that 15 years ago, almost to the day, was the birth of looking at differential geometry in M cross R. It happened in Berkeley at the end of a meeting. I first heard about it at a swim club where Harold and I were swimming. And Harold said to me, you got to do this. You got to look at this. And I heard him, and I said, Jesus Christ, what is he talking about? But he persisted. And even the simplest things you now know about surfaces in M cross R, for example, harmonic coordinates, were tough to figure out. And this insistence on the part of Harold, 15 years ago, when he was a young man of 60, has transformed the world in which you live. Some of you were born into this world. And there are lots of reasons I'm grateful to Harold, but this is one of them. He has created a world around us that's very rich, and it has helped solve problems that have nothing to do with just studying the geometry of these spaces. One of them is this one that Martin, Jose and Brian and I did. We got helicoids in R3 by getting them in S2 cross R and taking limits. I'm sure we wouldn't have even thought of this idea if it hadn't been for Harold's insistence and the world that came out around. So Harold, happy birthday. I wish you were still 60, but thank you very much.